Here is a differential equation application. Differential equations are actually used in a lot of areas of engineering and biology. And you'll see here a really good example of where we actually model differential equations. And this is actually a really good example because in the next video, we're going to talk about 3 different types of growth models. And actually, this is one of them. So let's try out this problem. A medical examiner called to the scene of a murder will usually take the temperature of their body. So the corpse cools at a rate proportional to the difference between its temperature and the temperature of the room. If Y of t is the temperature in degrees Fahrenheit of the body t hours after the murder, and if the room temperature is 70 degrees Fahrenheit, then Y satisfies this differential equation. So basically, this one tells you kind of like, whoops, I'm not writing anything. This kind of tells you kind of like the rate at which the body is cooling down, and then here is the initial. So we know that the initial temperature of a human is just 98.6 degrees Fahrenheit. So what we want to be able to do is solve this differential equation. So this is also an example of Newton's law of cooling, but I mean, if you are interested. So the first thing that we want to do is we want to solve this differential equation. So we know that y prime is equal to negative 3.2 y minus 70. And we also have an initial condition of this. So we're going to have a c value, and we're going to try to solve for that c value. So the first thing that we want to do is kind of just use separation of variables. So let's change this y prime to dy over dx. No, it will be dy over dt, because notice that now we don't have an x, we have a t. Okay, so it's dy over dt. And this is going to be equal to negative 3.2 y minus 70. Okay, so the first thing that we can do is you can move the dt over. So let me move this dt to the other side. So I'm left with dy is equal to negative 0.32 y minus 70 dt. And then lastly, what you want to be able to do is move the y over. So I'm going to divide by y minus 70. So this is going to go away. So I'm left with 1 over y minus 70. dy is equal to negative 0.32 dt. Notice that even though I don't have a variable on the other side, it's still a constant. Okay, so I could have easily moved this negative 0.32 to the other side as well, but I think that this is going to be a little easier to work with. So you don't necessarily have to have a variable right there. Okay, now because we separated all of this out, now what we can do is just take the integral to both sides. So this is just going to give me the natural log of the absolute value of y minus 70 is equal to negative 0.32 t, and then I have a plus c. We're going to get rid of that natural log by exponentiating both sides. So I'm going to take an e to both sides. So this is going to give me the absolute value of y minus 70 is equal to e to the negative 0.32 t plus c. Remember that we can do that little trick that we did last time, which is just basically, let me go ahead and put it down here. We can do y minus 70 absolute value is equal to e to the negative 0.32 t times e to the c. Okay. This is just a constant. Let's just call it c. So we're going to have absolute value of y minus 70 is equal to c e to the negative 0.32 t. This absolute value just gives me plus or minus. So y minus 70 is equal to plus or minus c e to the negative 0.32 t. Notice that this is just going to give me another constant. So we have y minus 70 is equal to constant c e to the negative 0.32 t. And then we finally just add the 70 over. So y is equal to c e to the negative 0.32 t plus 70. Okay, so we finally have our general solution of this differential equation. And now what we want to be able to do is solve for this value of c. And the way that we solve for the value of c is just simply by just using this initial condition. So remember that this is just basically y of t is equal to c e to the negative 0.32 t plus 70. So now we're going to plug in 0 for t, c e to the negative 0.32 times 0 plus 70. Y of 0, well, that's just equal to 98 28.6. Then we have C. This is just going to give me e to the 0, which is just 1. So e to the 0 is just 1 plus 70. And then we just subtract by the 70 over. So what I'm left with is that C is equal to 28.6. Okay, so my differential equation, y is equal to 28.6 e to the negative 0.32t plus 70. Okay, so this model is going to help me figure out what time the murder took place, because now I can take any time and I can try to figure out what the temperature is. Okay, so at time equals 1, time equals 2, time equals 3, I can figure out what the temperature is using this particular model. Okay, so now using this model, let's do part B. Part B says use part A to estimate how long ago the murder took place if the temperature of the body is 80 degrees Fahrenheit. So if I took the temperature of this body, okay, and it was 80 degrees Fahrenheit, I can try to estimate how long ago the murder took place. So I know that my equation, y is equal to 28.6 e to the negative 0.32 t plus 70 is basically how I'm going to figure out my temperature. My temperature is y, because that's what they told me, that y of t was the temperature. Okay, so basically I'm solving for the value of y, and then I knew, sorry, y is 80. Okay, there's just a temperature. I want to be able to find the value of t, how long ago that took place. So you have 28.6 e to the negative 0.32 t plus 70. Okay, and now all we got to do is solve for t. Now this just becomes a pre-calculus problem. Okay, so all we got to do is solve for this exponential, so minus 70 to the other side. So I'm left with 10 is equal to 28.6 e to the negative 0.32 t. Then let me go ahead and divide by 28.6. This goes away. So I'm left with, I'm just going to leave it as is, 10 over 28.6. That way it's I won't lose a lot of decimals. Okay, so I'm left with e to the negative 0.32 t. In order to solve this problem, we just have to take the natural log to both sides. So you have the ln of 10 over 28.6 is equal to, the ln and the e is just gone, so you're left with negative 0.32 t. And then finally, let's just divide by negative 0.32. So this goes away, so I'm left with t is approximately equal to, so this is something that you can put into the calculator, and what I'm getting is 3.28, and this is in hours. So basically what this tells me is that this murder took place 3.28 hours ago, and given that the temperature of this corpse is 80 degrees Fahrenheit.